So coming back into what we were doing with discrete distributions, and I wanted to mention one common, kind of the most common or most fundamental common mistake in probability, because a couple of the TFs mentioned that this is coming up on the homework, which I'm not surprised about, because this is like very fundamental. It's trying to understand the difference between a distribution and a random variable, right? That's what we've been talking about, but it's subtle at first, so you have to keep practicing that. So this is what I call sympathetic magic. Sympathetic magic is what I call the mistake of confusing a random variable with its distribution. So an example of that is that's come up on some of the homeworks is you have a sum of two random variables and kind of just blindly saying the PMF of the sum is the sum of the PMFs or something like that. That is, you're supposed to be adding random variables, and if you instead add PMFs, it's just makes no sense at all. So that's confusing the random. Adding random variables is not the same as adding PMFs, and in fact, for that PMF case, it really makes no sense at all, because if you did, P of x equals x, let's say I had x and y. We're going to talk a lot more later in the course about how do we deal with sums of random variables. But we've already talked about it to some extent. Remember, we spent a lot of time about the sum of binomials. The sum of independent binomials is binomial if they have the same p. We proved that in about 3 different ways. And we talked about dealing with x plus y by conditioning on x. So we have talked a little bit about that. We're going to do more later. So we have different methods for dealing with that, but we never said, well, take p of x equals x plus p of y equals y. All right, that's the PMF of x plus the PMF of y. And somehow this is supposed to relate to x plus y. Well, first of all, if you add up two probabilities, there's no reason from what I wrote to think that would still be less than 1, right, or less than or equal to 1. That could easily exceed 1, first of all. And secondly, this thing is a function of x and y, little x and little y. But if we want the PMF of x plus y, then we're thinking of x plus y as our random variable, so we should have a function of what's the probability that x plus y equals little t, or something like that. So you can't do things like that. Similarly, if you later we're going to deal a lot with what happens when you transform random variables. So if I have a random variable x and I want to cube it, it doesn't mean that I somehow cube its distribution or its PMF or something like that. You can't do things like that. So as a general, there's a famous saying in semantics that the word is not the thing, the map is not the territory. And that's exactly what this mistake is. So just to push this analogy a little bit further, the map is not the territory. This is like really an obvious piece of advice. Like, it's very rare that I've seen someone confuse a map with the territory, right? You don't usually like put the map on the floor and start walking around the map thinking that you're exploring the territory. That's the map, that's the territory. We don't make that mistake. Here, though, when we're talking about random variables and distributions, it's more mathematical, it's a more abstract thing, and people do make that mistake all the time. So the mistake is completely analogous. It's just in this context, it's somehow the human mind easily does that, and in the map territory context, it's not such a big deal. Here's an analogy along these lines that I like even more. Think of the random variable is a house. RV corresponds to house, and the distribution is the blueprint for the house. Okay? So most of you probably don't try to live inside a blueprint, right? it's the same thing. And I like this analogy even more because now we can think of if you have one blueprint, you could use that. You could build many houses from the same blueprint, right? Just use the blueprint and build it in different locations. So you can have as many random variables as you want, all with the same distribution. They could be IID, which would mean they're independent with their same distribution, or they could be dependent, but they could have all the same distribution. There's no problem with doing that. So let's actually call this a random house. The distribution is a blueprint for building a random house. The random variable is one of those random houses. So the blueprint means, it's not just saying, you know, put this door here and put this wall here. It's saying, you know, you randomly choose whether you have like a blue door or a red door and with certain probabilities. This is specifying all of the probabilities you need for different choices for how to build the house. The random variable is the house. Okay, so that's just a very, very common mistake that's it's sort of like a meta mistake or like a class of mistakes because there are many, many individual mistakes that I attribute to this. So that's why I'm suggesting to be careful about that. All right, so now coming back to our discrete distributions, we only have one more famous discrete distribution that we need for this entire semester, and that's called the Poisson distribution. So that's the main topic for today. I want to show you, first of all, what is it? Secondly, why is it important? Arguably, the Poisson is the most important discrete distribution in all of statistics. Depends how you define importance, but I think you could make a pretty good argument for that. It's named after Poisson, who was a famous, brilliant French mathematician who was the first or one of the first people to start working with this distribution. In the 1830s, he was doing this. And so first, let's write down the PMF, and then see you know what's so great about this. Okay, so here's the PMF. We want to know what's the probability that x equals k. K is a non-negative integer here. So unlike the binomial, which is bounded between 0 and n, Poisson could take any non-negative integer value, and the PMF is just e to the minus lambda, lambda to the k over k factorial, where k, as I said, is a non-negative integer, 0 otherwise. And lambda is the parameter. And I call it a rate parameter for reasons that will become clear at some point. But for now, just think of it as this is a one-parameter distribution with parameter traditionally called lambda, but you could call it whatever you want. That's just the parameter of the distribution. But lambda is the most common name for that particular parameter. So lambda is a positive constant. Lambda could be any positive real number. That's the parameter of the lambda. That's the parameter of the Poisson distribution. All right. So, I mean, I just wrote this thing down, but that doesn't mean that it's useful for anything. So why do I say this thing is so important? Well, before we can do that, first let's check that this is a valid PMF. That is this actually a PMF? Well, they're non-negative, so the only thing that we need to check is that these numbers add up to 1. And that's very easy because if you add up e to the minus lambda, lambda to the k over k factorial, e to the minus lambda is a constant, so that just comes out. The sum of lambda to the k over the k factorial, hopefully by now everyone recognizes that that's the Taylor series for e to the lambda. So this is e to the minus lambda, e to the lambda equals 1. All right, so basically all we did was take one term from the Taylor series for e to the lambda and then put a constant in front so that they add up to 1. So that is a PMF. And while we're doing a calculation like this, we may as well compute the expected value also. So let's find the mean, e of x. And as notation, we would write x as Poisson lambda, and we'll usually just abbreviate that to POIS. Okay, so let's find the expected value. Well, remember, the expected value is the sum of the value times the probability of the value, right? So I'll take out the e to the minus lambda because that's just a constant. So what we're doing is just adding up k, that's the value, times the probability of the value, which is e to the minus lambda, lambda to the k, over k factorial, from 0 to infinity. But when k is 0, this is 0 anyway, so we may as well start the sum at 1. So let's go from 1 to infinity. And notice we have k over k factorial. Well, k factorial is k times k minus 1, k minus 2, blah, blah, blah. So the k cancels one of the k's. K cancels the k here, and we're left with k minus 1 factorial in the denominator. So that's really just lambda to the k over k minus 1 factorial. Now it's not a calculus problem. It's just a pattern recognition problem at this point. When we see this thing, it should remind us of what we just did, basically, right? That's the Taylor series for e to the lambda. This series looks a lot like this series. The only difference is that we have a k minus 1 factorial, not a k factorial, and we're starting at 1 rather than 0. So to make this match up better, let's just take out one of the lambdas. So I make this lambda to the k minus 1. Lambda is just a constant, so you can put back lambdas all you want. I put it that way so that now this k minus 1 matches this k minus 1. Now, if we want, we can just let j equal k minus 1 at this point, or just write out the first few terms and just directly see this is exactly the Taylor series for e to the lambda again. So therefore, this is just lambda e to the minus lambda e to the lambda equals lambda. So that's a very useful, easy to remember result, that a Poisson lambda has expected value lambda. Okay? So, memorizing formulas is not that important in this class, but this one is useful and very easy to remember. The mean is lambda. Okay. So that's the expected value of a Poisson. Now, why do we care about the Poisson, though? So let me just mention a few examples where the Poisson is used. It's the most widely, in practice, it's the single most widely used distribution as a model for discrete data in the real world. So often used for applications like, well, let me just say what the general application is. Applications where we want to count something. It's used for counting because it's non-negative integers, or counting number of something. Let's say number of successes, but again, just like in the binomial, we can define success and failure like in a very general way. So I'll just put successes in quotes because we could define that in many different ways, but just to have a word. We're counting the number of successes where we have a large number of trials. So there are a large number of things, each of which could lead to success or failure, but the probability of success for each one is small, right? So let's say we had 10,000 trials, but each one only has probably 1 over 10,000 of success. Well, we immediately know that the expected number of successes is 1, just using linearity and indicator random variables. But it's that kind of thing where we have large number of trials, small probability for each one. Okay? So that's the general setup. And each one with a small probability of success. So some examples would be like number of emails that you get in an hour. I'm not claiming this is exactly Poisson. I'm saying that as an initial, right, to check whether the number of emails you get in an hour is a Poisson or not, you'd have to go collect data and try to see, like, that's an empirical question. That's not a mathematical question, okay? But the claim is that this would be a reasonable starting point as a model for that in some cases it may be very good, in other cases it may be bad, but this would be a reasonable first approximation. That's what I'm saying, not as an exact distribution. So why would the number of emails, just intuitively, why would that be Poisson? Well, imagine that there are a large number of people who potentially could email you in that 1 hour block of time, okay? But for any individual person, unless you have someone who's constantly emailing you like every few seconds all day, in that particular block of time, it's fairly unlikely that any specific person will email you. But if there are a lot of people who could email you, then that's balancing it out, right? So we're defining success to be, for each person, whether or not they email you in that hour. There are a lot of people who could email you, but each one is fairly unlikely. That's the setup. Change email to phone calls or whatever you want here. You can make up as many examples as you want. Another famous example is like the number of chocolate chips in a chocolate chip cookie. Number of chips in chocolate chip cookie. Now let's think about how do we interpret that one. Well, it's like a cookie is made up of bunches of, what do you call them? There's like stuff in the cookie, right? Now most of the stuff is not chips, right? Well, I guess, start with some cookie dough and there's some number of chips you put in. Now each little bit of dough is probably not a chocolate chip, right? It's very sad. But there are a lot of them, right? And each one, in each little, little segment of the cookie, it may be a chip there, maybe a chip there, maybe a chip there. Most of them are not, but there are a lot of possible locations on the cookie where there could be a chip. So usually you at least get a few. Not enough, but you get a few, okay? So that's why that's going to be approximately Poisson. And so on and so on. You can go on, as many examples as you want. So this is, more serious examples would be like number of, earthquakes, let's say in a year in some region. Again, I'm not saying that's exactly Poisson, but that would be a reasonable first choice of a distribution because on each particular day, it's not likely that there's an earthquake, but there are a lot of days in a year, and so there may be a few earthquakes, right? So that kind of thing would be approximately Poisson. We haven't proven that yet. We're gonna show, not in complete generality, but we're gonna show a result along these lines that shows where this distribution comes from mathematically. Okay, but right now this is just intuition and like how is this used? So these examples, again, I'm not saying they're going to be exactly Poisson. And in fact, if you look at a lot of cases where the Poisson is used, actually there's some obvious upper bound. And whereas here we're going up to infinity, that there's no upper limit. So most cases it's clear that the example will not be exactly Poisson, but it's an extremely useful approximation in a lot of problems. And that's called the Poisson paradigm. Or just more simply, just call it Poisson approximation, Poisson paradigm, but just to say that in words, let's say we have events A1, A2, blah, 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 through AN. Suppose we have a lot of events, right? And they are with P of AJ equals PJ. So we have N is large, and so we have a large number of things that could happen, but each one is unlikely, right? That's what I was talking about. I'm just trying to write this a little more mathematically right now. Then, so the PJs are all small. Okay? And now we have to say something about independence. So the events are either the nicest case is where they're independent. But actually, this result is even more general, so that they could be weakly dependent. And I'm not going to give we have a mathematical definition of independence. It's very difficult to mathematically define weakly dependent. The intuition is just that independence, comes in degrees to some extent, and that independence, says that learning, for example, learning A1 through A3, whether they happened or not, independence would say it gives us no information whatsoever about A4, A5, A6, and so on, whether they occur, right? That's what independence would mean. Weak dependence would mean we could get a little bit of information. They have to quantify, what does it mean to have a little bit of information? Well, the easiest way to think of it would just be that, let's say I knew that, for example, if knowing that A1 happened, suppose that tells us nothing about whether A3 happened. But if we know that both A1 and A2 happen, maybe it makes it a tiny bit more likely or less likely that A3 happened. So it's slightly, slight deviations from independence. That's what we're talking about. Then the claim is that the number of events that occur, number of the AJs that occur, is approximately Poisson. And we can figure out right now what lambda would have to be for that to make sense. We just showed that lambda is the expected value of the Poisson, so it makes sense that lambda should be the expected number of how many of these events occur, but by linearity, even if they're dependent, by linearity, the expected number of events that occur is the sum of the pj's. So lambda should be the sum of the pj's. Okay, this is approximate. So this is also called the Poisson approximation. That's the same thing as a Poisson paradigm. So one case that we've looked at a lot is the case where all the events are independent and all the pj's are the same. They're all equal to the same p. In that case, we just have Bernoulli trials with the same p. In that case, we know that the number of events that occur is exactly binomial NP, okay? And in a minute, we're going to prove that, in fact, the binomial NP does converge to a Poisson when we get n get large and p get small in a certain way, okay? But this is much, much more general than just for the binomial, because this is saying that Poisson is going to work well even if the p's are different, right? Remember, for the binomial, we had independent trials with the same p. Here it says the p's can be different, and they can be at least a little bit dependent, and it's still going to be a good approximation. Okay? So, all right. So now let's explore the connection with the binomial more. So what we want to show is that the binomial converges to the Poisson. So if we have, let's say x is binomial NP, and I want to show how does this relate to the Poisson. Like, because that formula for the Poisson, well, it reminds us of a Taylor series for e to the x, but what does that have to do with probability? Whereas we know the binomial is something very fundamental. So we start with the binomial NP, and we're going to let n go to infinity. That's just the mathematical way of capturing the fact that we want a large number of events. So if we want to use this as an approximation, well, in practice, n is still going to be some finite number. And our hope is that here, mathematically, we're letting n go to infinity, and as an approximation, what we're hoping is that n is, even though it's finite, n is large enough so that these kind of limits kind of kick in and work well. So we're going to let n go to infinity. We're going to let p go to 0. We're taking two limits here. That's the way to do something that's mathematically precise. And in general, they could go to this could happen in different rates that we'd have to deal with. But the case we're most interested in right now is where the product, let's call it lambda equals NP, is held constant. And we can do more general versions than this, but this is a natural one to start with, because remember the expected value of a binomial NP is n times p. the expected value of a Poisson lambda we just showed is lambda, so it makes sense to set lambda equal to NP to try to explore the connection between those. So this is telling us that, P is going to 0 at the same rate as n is going to infinity, because we're holding the product constant. All right, so now we want to show that the PMF converges. So find what happens to the PMF. What happens to the probability that x equals k, which we keep seeing is n choose k, p to the k, 1 minus p to the n minus k. So we want to know what happens to this thing, where we're treating k as fixed. As we're letting n get very large, p get very small, but then we want to look at one specific value, for the PMF. So we're letting k stay constant. All right, so that's what we want to do. And then at this point, we just need to do some algebra and a little bit of calculus. So let's try to right now this is written as a function of p and n. It's going to be easier to deal with if we get everything in terms of n. And so conveniently, we have p equals lambda over n, so we can write everything in terms of n. And let me also write n choose k a different way. N choose k is the number of ways to choose k people out of n where order doesn't matter. So that's the same thing as n times n minus 1, blah, 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 n minus k plus 1. That would be choosing a committee in a certain order, where order matters. Then we divide by k factorial to reflect the fact that order doesn't matter. So that's just exactly the same thing as n choose k according to the story, or you can check that easily just using factorials. I'll plug in p equals lambda to the n, p equals lambda over n, so that's lambda to the k over n to the k. I'll just stick the n to the k over there. And then we need to deal with this thing, 1 minus p, which is 1 minus lambda over n to the n minus k. And this kind of minus k thing is, I'll just separate it out so we can deal with that later, because k is fixed. It looks nicer to me this way. All right, so that's just a little bit of algebra. Now let's take the limit of this. The k is fixed, so k factorial here just stays as k factorial. Now let's look at, and lambda to the k is also fixed. So we have a lambda to the k over k factorial, which is pretty encouraging, because we want that for our Poisson. Now, that's lambda to the k over k factorial. Let's look at this stuff with the n's. On top, we have k terms. I've written a product of k terms where it decreases by 1 each time. And the bottom is n times n times n k times. So let's just match up terms. Take the first n from here, match that with that n. The second one, match it with the n minus 1. The third one with the n minus 2, and so on. Each of those terms goes to 1. As for example, one of them might be n minus 7 over n, but I'm letting n go to infinity, so the 7 is completely negligible. So this stuff with the n's just goes to 1. Lastly, and then this part, n goes to infinity, so this is going to 1. 1 to the negative k is 1, because the exponent is fixed, so this part just goes to 1. Lastly, we just need to consider this part. That part, I just have to remind you of a general useful limit, that 1 plus x over n to the n goes to e to the x. Sometimes this is even taken as the definition of e to the x. This is probably the most important limit for e to the x. I think of this as the compound interest formula, because what this is, if you have like money in a bank that's being compounded a certain number of times per year, and as you let the rate of compounding increase, in the limit you have continuous compounding, you have exponential growth. So you can, if you haven't seen that limit before, I think it's on the math review, or Bo did it in his math review, Or just use L'Hopital, take the log, use L'Hopital's rule, so that's a famous, useful limit. So that goes to e to the x. So therefore, this thing goes to e to the minus lambda. And that's just the Poisson PMF evaluated at k. Okay? So that shows that binomials converge to Poisson when we do it in this way. Another example that I like to think of, just as more intuition on this, is counting the number of raindrops that fall in some region. I don't know why I like this example, but I just find it very, very intuitive for understanding the connection between binomial and Poisson. So I'm just going to draw a quick picture. So this is the raindrop example. So imagine we have like a piece of paper, which I'll represent as just this rectangle, and imagine that well, the board is vertical, but imagine we turn this horizontal, and then imagine we're outside and it's raining on this. We want to know how many raindrops hit this piece of paper in say, 1 minute, okay? Well, one way to think about that problem would be to take this piece of paper and, break it up into lots of little squares. So, draw as many as you want, but I'm just going to draw like a grid, and imagine that we've broken it up into like millions and millions of tiny little squares, okay? Now, for each individual, and I want to count the number of raindrops in some time interval, for each individual square, if we break this up into tiny enough pieces, each individual square is unlikely to get a raindrop hitting exactly in that, if we make them small enough, right? So each one is kind of unlikely, but we have a huge number of little squares, okay? So we are going to get some raindrops hitting this piece of paper, probably, right? And lambda is going to be a measure of the intensity of how hard the rain is coming. And so let's think, should we use a binomial distribution for this? Well, if we assumed that every one of these squares, whether it gets a drop of rain or not, is independent of all the others, and if we assume that they all have the same probability p, then it would be exactly binomial, okay? But, I mean, I don't know enough about rain to answer this or not, but I'm guessing it's not really exactly independent, but it seems like a reasonable approximation to treat them as independent. Oh, one other complication with the binomial. With the binomial, we would be assuming that each one of these squares can only get either 0 or 1. Now, there's some tiny chance that 2 raindrops could fall into one of these squares. So it's not going to be exactly binomial, but even if it were exactly binomial, if we had binomial of like, 1 trillion, comma, and then some tiny number, that's very, very hard to work with. Certainly very hard to work with by hand, but even on a computer, computers are going to have a lot of trouble handling, even 1,000 factorial, or you're going to run into some computational difficulties. Binomial has a lot of complications to it, where the Poisson is much simpler to deal with. So a Poisson approximation seems reasonable here because we have a huge number of little squares. Each one is very unlikely. All right. So let's do one example, like with the birthday problem type of setup. And you have one on the next homework 5, related to this too. Let's do the problem of triple birthday matches. As we worked out, the exact answer for the birthday problem of what's the probability that at least 2 people have the same birthday when you have a group of people. Okay, but now suppose, we have, so the example is, let's say we have n people, and we want to know the probability that there are 3 people with the same birthday. And we only need to do it approximately. In general, in this course, assume that every answer you give needs to be exact unless I say, give an approximation. In this case, I'm saying find an approximation. Find the approximate probability that there are 3 people. That is, you can find some, maybe there's more than 3, maybe there's 4 people who all have the same birthday, but you can find some group of 3 people who all have the same birthday. Okay, that's the problem. So if you try to do this in a way that's analogous to how we solved the original basic birthday problem, this is actually pretty difficult. Very difficult. You can try it, but it's not going to be nice. Okay? But with a Poisson approximation, this is actually should be pretty easy. So let's go through how to do that. So we want 3 people to all have the same birthday. Let's just think about what does that mean. And first of all, does that does this Poisson paradigm kind of seem appropriate for this problem? Okay, so let's think about that. Well, first of all, I didn't say what n is. So if n is 2, then it's 0. And if n is 3, that's a very small number. This is not going to work so well. So assume n is reasonably large, but n does not have to be. A key point here is that n does not have to be very, very large. The more relevant, just like in the birthday problem, part of the intuition, why do you only need 23 people when there's 365 days in a year? Well, 23 is a pretty small number, but 23 choose 2, is 253, is reasonably large, right? So the more relevant quantity is n choose 3. So even if n is, n should at least be, 10 or 20 or something like that. N does not have to be in the hundreds for this to work well. Because even with, some double-digit n, when you do n choose 3, it's going to be pretty large, right? Okay? So there are n choose 3 triplets of people, right? Assume that the people, as usual, we assume the people are labeled as 1 through n. Take any subset of 3 people. I call that a triplet. For each triplet, you can ask the question, does that triplet have the property that all 3 of them have the same birthday or not? Right? So we would create an indicator random variable for each one. Let's call that I sub ijk, where if you have people ijk, where I is less than j less than k. So ijk are any numbers between 1 and n in increasing order, just to avoid repeating the same thing multiple times. Then we define this indicator to be 1 if they all have the same birthday. Okay? So actually, I didn't write it here, but at this point we know the expected value. We know the expected value exactly. Expected value of the number of triple matches. We get that immediately by indicator random variables, linearity, and symmetry. That is, it's n choose 3 of these indicators. And for each one, now I'm imagining that I have the first 3 people, just for concreteness. First person can have whatever birthday, and the second person has to match the first person. That has probability 1 over 365. And then the third person also has to match, so it's 1 over 365 squared. That's exact. So that's the exact number of triple matches. Notice, though, that if there's a group of 4 people who have the same birthday, we are counting that as, for each set of 3. So there are 4 choices of 3 people out of the 4, and we're counting that as 4 matches. Okay, so that's the exact answer for the expected value. But I said find the approximate probability, I didn't say find the exact expected value. Okay? So now we're going to use the Poisson approximation. And so let's let x equal number of triple matches. There's no possible way that x could be exactly Poisson, because the number of triple matches couldn't be more than the number of triplets. So whereas the Poisson has no upper bound. Okay? But we're claiming that it's approximately Poisson And so let's talk a little bit more about why is that approximation valid. And lambda is what we just computed. It's the expected value. So let's talk about why is that a reasonable approximation. Again, I'm assuming n is reasonably large. It doesn't have to be very large. So why is that valid? Well, even if n is like 15 or 20, n choose 3 is pretty big number. Okay, so the number of the number of trials is fairly large. The probability of success for each trial is a group of 3 people, is very small, right? Very, very unlikely. Okay, so we have a large number of possible triple birthday matches. Each one's unlikely. And then the other question is independence. Well, we don't exactly have independence here because, like, for example, I1, 2, 3 and I1, 2, 4 are not independent, for example, because if this event occurs, that is, if this equals 1, it means the first 3 people all have the same birthday. And now I want to know whether people 1, 2, and 4 have the same birthday. Oh, we just kind of got a head start there. We already knew if we know that this event, that this indicator equals 1, then we're already kind of partway there. So they're not completely independent. But this would be an example of weak dependence in the sense that the probabilities are small anyway, first of all, and secondly, that's a head start, but we still need person number 4 to match. And that's just like for a specific case where I define these with some overlap, but for example, I1, 2, 3 and I4, 5, 6, those are independent. So there's not that much dependence there. So this seems like a reasonable approximation, and then to finish the calculation, well, we would just say, we want to know what's the probability of at least one triple match. And as is often the case, it's easier to do the complement, so that's 1 minus the probability that x equals 0. And as an approximation, that's going to be 1 minus e to the minus lambda to the 0 over 0 factorial, which of course is just 1 minus e to the minus lambda. So that's 1 minus e to the minus lambda, where lambda is this. So notice that this is something that you could calculate easily, using a calculator or a computer. You don't have to do like some complicated sum and evaluate a lot of binomial coefficients and all that stuff. So this is very, very useful for getting nice, quick approximations. All right, so that's the Poisson distribution. That's our last discrete distribution, so congratulations on that, and I'll see you next time.